So there's two kinds of charge to think about in these problems. There's free charge and bound charge. So first let's do free charge. Free charge is usually the excess charge that you put on a conductor or you just place in space that causes the effect you're studying. So in this case, what created this whole problem is the fact that we put these two charge planes here to create the original external field. So that's the free charge. It's usually an excess charge, right? So if you think of this as being a metal plate, this is the amount of charge you added to the plate. Or if it's hooked up to a metal plate to a battery, this is the charge that flowed out of the battery. Or sometimes we just say there's a plane of charge in space. That would be free charge. But what happens is when you bring a dielectric into the field created by the free charge, it creates something called bound charge. Okay, so the polarization, remember we created a polarization field inside this dielectric because of the electric field. The polarization results in bound charges on the surface. Okay. It sort of makes sense physically if you think about it. So really, we're not doing a microscopic model. So I drew atoms and molecules before, but forget the atoms and molecules. We're doing a continuum. So if the material is a continuum, we can acknowledge it has a bunch of positive charge in it and it has a bunch of negative charge in it. But just think of those as continuous blocks of charge that can sit on top of each other. And when they do that, they're neutral because there's the same amount. And they're perfectly smooth, no matter how far you zoom in, whatever scale. You never see atoms or molecules or electrons or protons. It's just smooth. If we polarize it, what it means in that case is the smooth, continuous positive charge moved a little bit that way. The smooth, continuous negative charge moved a little bit this way, and they get a little bit exposed on the surface. So you get a little bit of a charge density over here, positive, and you get a little bit of negative over here. And it's just as real as the free charge, right? You think of free as excess charge, that's real, right? You think this, well, this was neutral, so there's not really any charge here. Yeah, there's charge there. Remember my Teflon rod, it had 1 million coulombs of charge, right? There's a lot of charge in something that's neutral, it's just covered up. So when you polarize it, you uncover a little bit of the charge. So mathematically, what that is you get sigma, you get a charge density on the surface, sigma bound, and it's equal to the polarization field dotted with the normal unit vector of the surface, okay? Because remember, what was our unit for the polarization field? It was coulombs per meter squared. It has the unit of a charge density. So here, we're just saying that you guys got to take the dot product between the P and the N. And in our case, we're doing one dimension, so N is just normal to the surface anyway. So in this one-dimensional case, the charge density is simply equal to the magnitude of the polarization field. And the charge density then we could label as here on this side we have plus sigma, and I'll put B, to remind you that's the bound charge, and minus sigma B. This is simple in this one-dimensional case, but this is generally true. So you can derive this by just taking a polarized dielectric and calculating the field it creates, and do all this complicated vector calc to get this general expression that's true for all geometries. In this case, it just means we get plus sigma B and minus sigma B. They're not necessarily equal to sigma free, right? That's not something I'm trying to say is true. That would be true if this were a metal. This is a dielectric. Some amount of charge density builds up. It depends on how polarizable the material is, okay? So let's think now. What we're really going to do is apply Gauss's law, but we're just going to think about it. We're not going to write down Gauss's law. And let's think, what does that do to the fields? So let's look. The field outside the dielectric remains E, I'll still call it E external because we're outside the dielectric. It remains sigma, which I'll now call sigma free, over epsilon naught. And since I put a vector hat on it, I'll say I hat. Okay? Now, why does it do that? Well, we know these two created that field. It's two charged planes. Each one makes sigma over 2 epsilon naught, so you add them together. We've done that when we talked about capacitors. But now here we have the same thing again. We have two planes of charge, equal and opposite, and we know what they do. They make a field inside, but they make no field outside, right? Because the field of this one and the field of this one is the same right here, but they're opposite direction, they cancel. It's the same reason that these two planes don't make any field out here, right? They just make it in between. So because we have a one-dimensional system and everything is symmetric and everything is equal on both sides, the field outside the dielectric is not perturbed. That's only true for this one-dimensional simple system. Okay, in other systems, the field outside the dielectric can be perturbed. That's the field inside. Let's look at the field, I'm sorry, that's the field outside. Let's look at the field inside the dielectric. And the field inside the dielectric, E internal equals what? So now, inside the internal field, we basically just have to sum all the fields. Right? Electric fields obey superposition, so it's E external sigma free over epsilon naught minus sigma bound over epsilon naught. Epsilon naught. Because you can see the field created by the bound charge goes the other way. So it's going to make the field internal inside smaller, and if I had to put a unit on it, I'd make it go that way. Okay, so we're making a little progress.